And we're back one more time, and this time we're going to be just looking at some blank or some tables, and we're going to try to figure out, what is this? Go away. We're going to try to figure out uh, what's happening here. So let me make this a little bit bigger this way. There we go. Use differences to identify the type of function represented by the table of values, then label which type of function each table of values models. And if it's linear or exponential, we're going to try to come up with the equation. All right? That's what we're going to do. And then if you'll notice on the next page, page 69, you have 16 problems like this. So for you, it's going to be linear, quadratic, exponential, or neither. All right. So linear, quadratic, exponential, or neither. In other words, it doesn't have same first differences. It doesn't have same second differences. It doesn't have a constant multiple down the y value. It's something else, right? It's another function we haven't studied. Or maybe it's not a function at all. It's just a relationship that's not linear, quadratic, or exponential. So let me get there we go. Let me get the pen to pop up. And I thought I had all this ready to go. It is kind of rainy and wet outside. I sure was hoping that it would be warmer today. I got my exercise clothes on. I was going to go out and run at lunch, and then it's rainy. So maybe tomorrow. All right. I hope it's hard to when it's not necessarily pretty. It's hard to run and play, so to speak, outside. Let me see if I can't move this thing. Not really what he is about, but I don't need him. So go away. Okay. So here we are. Let's just look. I'm going to figure out which kind of function it is. So let's see. X is changing by 1 each time. Okay. +1, +1, +1. All right. So let's see if we can see how the y values are changing from 5 to 8. Well, that's 3, isn't it? So that's 3. We'll look at first differences. From 8 to 13, that is 5. From 13 to 20, that's 7. From 20 to 29, that's 9. From 29 to 41, that's 11. Okay, so my first differences are not the same. The x values are increasing, the y values are increasing, but they're not increasing by the same amount each time. So what do we know? This is not linear. Okay, first differences. I know that it's getting bigger, but I don't know that it's getting really big really fast. So I'm not sure that it's exponential. In fact, when I look at these first differences, 3, 5, 7, 9, 11, what do I notice about those? First differences. Well, let's go back and take second differences and see. What's the difference between 3 and 5? 2. What's the difference between 5 and 7? 2. Between 7 and 9. 2. Between 9 and 11. 2. So the first differences gave me what? All odd numbers, consecutive odd numbers. And my second differences are the same. How about that? So what do I know about this table? It is quadratic. And that's interesting because usually when we see a quadratic table, we see the turning point. We see it increasing and decreasing, or we see it decreasing and increasing, right? But not in this one. The y values are just getting bigger. So we don't see the turn. We don't see the change in direction. But from the table, we can see what first differences are not the same, but second differences are. So it's quadratic. How do we know it's quadratic? It has same second difference. Okay. All right. Let's look at the next one. The x values are all increasing by 1. Okay, so change in x is 1. Let's look at the change in y. 32 to 16. What's happening? Well, it's going down how much? 16. 16 to 8, that's what? Going down 8. Well, we already know it's not linear. 8 to 4, that's going down what? 4. 4 to 2, that's doing what? That's going down 2. 2 to 1, that's doing what? Going down 1. Hmm. So we know it's not linear, it's decreasing, but to me, it seems to be decreasing a bunch. Don't you think? 32 to 16, that's like, wolf. Okay. So notice over here, these values are not the same, but if we look over here, wait, look, 16, it kind of looks like I'm repeating the first y values, doesn't it? Let's go back and look at second differences. If second differences are the same, then it's quadratic. So 16 to 8 is increasing. That's increasing this time, and that's increasing by 8. 8 to 4, that's increasing by 4. 4 to 2, that's increasing by 2. 2 to 1, that's increasing by 1. Look at there. 32, 16, 8, 4, 2, 1. 16, 8, 4, 2, 1. 8, 4, 2, 1. Huh, how about that? The first difference and the second difference were actually just a strange repeat of the first y values. So you know what? I'm thinking this might be exponential. So let's go back and instead of subtracting, let's see, is there another way to get from 32 to 16? You might be thinking divide by 2, but we need to write it as multiplying. So let's say multiply by what? A half. A half of 32 is 16. Half of 16 is 8. Half of 8 is 4. Half of 4 is 2. Half of 2 is 1. Guess what this one is? Exponential. So with exponential, when you do the first and second differences, you see the pattern in the y value repeated. That's interesting. Okay. And I didn't show you that while ago. I just went straight to the multiplying factor. So that was my fault. Could we write an equation for this? Well, we can. We know that for exponentials, it's y equals what? AB to the x. We worked on that last week. A is the amount when y is 0. So when x is 0. So when x is 0, the y value is 1. So that means A is 1. 1 times, and what's it doing each time? It's multiplying by how much? A half. There we go. Okay. So what are we multiplying by? When we give the base value right here, we tell what the constant multiple is. B equals 1/2. That's what we're multiplying by each time. All right. Let's look at this one. My x values this time are changing by 2. 2, 2, 2, 2, 2. Okay. 2, 2, 2. What are my y values doing? Well, from negative 2.75 to negative 2, that's an increase of 0.75. From negative 2 to 1, that's an increase of 3. From 1 to 13, that's an increase of 12. From 113 to 61, oh man, that's an increase of 61 minus 10 is 51 minus 3 is 48. From 61 to 253, whoosh. All right. That is an increase of 253 minus 50 is 203 minus 10 is 193 minus 1 is 192. Aha. Well, are the first differences the same? No. Okay. So let's go back and find the second differences. Okay. From 0.75 to 3 is 2.25. From 3 to 12 is 9. From 12 to 48 is 36. from 48 to 192. 192 minus 50 would be 142, plus 2 is 144. Okay, guess what? These new values also appear to be what? First differences aren't the same, second differences aren't the same, but what do you notice? The y values are increasing rarely rapidly here. In fact, here it's hard to tell what we're multiplying by, but look here. 3 to 12. What is that? Oh, that's times 4, right? 12 to 48. Oh, that's times 4. 48 to 192. That's times 4. Even over here, 2.25 times 9, or 2.25 times 4 is 9, times 4 is 36, times 4 is 144, okay? So what am I multiplying by down the y column here? 4. You don't see it here because your x values are changing by 2. So that's kind of interesting, isn't it? Okay, so this is exponential. It is. All right. It's exponential. And do you see that they're getting very big very fast? So, and then what? We have continued exponential pattern in the first and second differences. So we had a quadratic, we had two exponentials, and then let's look at this one. My x values are changing, looks like by a quarter each time. Yeah, 0.25, 0.25, 0.25, 0.25. Okay, how about over here? So my x values are adding 0.25. My y values, 9/10 to 1 and 1/10. That's plus 2/10. And then this is what? That's not times 2. That's kind of what it looks like. This is plus 2/10 from 1 and 3/10 to 1 and 5/10. This is plus 2/10, plus 2/10, plus 2/10. So if you'll notice what's happening, I'm adding the same thing each time. Ding, 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 ding. That is the telltale sign for linear. So this is linear and it has same first differences or rate of change. And what would that be? Well, it is the change in y, remember, over the change in x. My change in y each time is 2/10. My change in x each time is 0.25. So that's actually 4/5, which is what that is. If you need to, let's don't leave the decimals in. Let's don't leave the decimals in the fraction. If you need to divide 2/10 by 1/4, and that is 4/5, which is the same as 8/10 or 0.8. Okay, so the rate of change m equals, if you divided that out on your calculator, which is how you'd probably be most comfortable, you would get 0.8. It's also equal to the fraction 4/5. If you think about this, this is what, 20 cents divided by 25 cents, which reduces to 4 out of 5. Okay, all right. So right quick before we're done, let's look at these. 10 times 1/3 to the x. The key on this is, where is x? X is in the exponent. If x is in the exponent, then it is Shazam, exponential. Y equals x plus 3 quantity squared minus 4. What's the key? The exponent of 2. If it's squared, it means it's a quadratic. You got it. Number 5, y equals negative 1/2 3 to the x power. Again, if x is the exponent, it is exponential. How about over here? Y equals 5 plus 7 times x. This isn't to the x power, it's just y equals 7x. That kind of looks like y equals mx plus b, doesn't it? Which means that it's linear. Yes, sir. Y equals -2 times x plus 5. Yep, linear. And then the last one, y equals 1/3 times x squared minus 4. What's happening to x? Is it in the exponent spot? No, x is being squared. X is being squared. So when x is squared, that means it's quadratic. All right, so let's try to come up with something here. Uh, we've got some all statements down here, and mine's a little bit covered up. Let's see, all linear functions have what? They have from the table, they've got constant rate of change. They've got y equals mx plus b. Yes, they got the line, constant. Ooh, I misspelled constant. Oh, how about constant slope? All quadratic functions have a what? They're squared. The exponent is squared. Y equals x squared. What's the parabola? It looks like a parabola, yes? And the table is what? Same, second, differences. Linear functions have what? Same, first differences. I should have written that down. And then the one that's covered up, all exponential functions have what? They have an x in the exponent spot. Their first differences aren't the same. Their second differences aren't the same. In fact, their first and second differences are usually a repeated exponential table. And what's the kicker on exponentials? Well, you go back and figure out it has a constant ratio. We're multiplying by the same number down the y values. So that is the end of the comparing linear, quadratic, and exponential. And your assignment is to look at the 16 tables on page 69 and decide linear, quadratic, exponential, or neither. You've got a few that are neither on there, so be careful. Do your best. Show up to the Zoom activity or the Zoom class meeting tomorrow. I'll post that information on Google Classroom, and you'll need to have the code to log into Zoom, which I will provide for you. Love you. Do your best. We're going to get through this, y'all. You are precious, and you are trying, and you're learning and growing, and I'm proud of you. So keep that in mind and know that we can get through this. All right? And we will. So